Welcome to Lesson 2 of Chemistry B from Mizzou Academy. I have a question for you. What's inside this jar? Most of the time when I ask this question to my students, they'll say water and ice. First, it's a little wrong to say water because in chemistry, as you know, most chemicals look like water. Quite a few do. In this case, however, it is water. It's also solid water, ice, and air. I hope that you said there's also air in that jar because this is what Lesson 2 is about, air, gases. We're surrounded by gases and we often take them for granted or we don't think about them because we are so immersed in them, we just don't think about them. So we're surrounded by these particles, they're bouncing around. More than 70% of them are nitrogen particles, but luckily we have about 21% oxygen particles that allow our cellular respiration to take care of itself so our bodies can keep homeostasis so we can survive. So we depend on those gases. We know gases exist even though we don't normally see them or smell them from all kinds of different empirical observations. And here's a simple demo that I just enjoy. Make sure you can see the flame. All right. And then in this measuring cup, I've got white vinegar. And then this bottle, I've got baking soda. I hope you've done this reaction before, but if not, do it with a responsible adult. See what happens for you. I've made sure that my candle is burning all right. And I'm going to very carefully add a little vinegar to my baking soda. I can tell a reaction's happening. You might be able to hear it, but you can see the bubbles. Anytime we make bubbles, we're producing a gas. In this case, the gas is carbon dioxide. What's something you know about carbon dioxide? There's lots of things, but one of them is it's more dense than air. So with any luck, my bottle is full of the gas carbon dioxide. I'm going to pour just the gas over the flame. Carbon dioxide also smothers fire, just like it smothers us, just like we need air in order for our exothermic cellular respiration reaction to happen. We produce heat. That is an exothermic reaction. Combusting wax is the fuel, also exothermic reaction, produces heat. Needs oxygen, right? Fire needs oxygen. So in some ways we say that even in ourselves we are burning. We are burning through our beautiful lives. We are a bright fire for people to look up to, right? Okay, keep your gases in mind. That's what the whole chapter is about. Most people say, hey, when I take chemistry, it's going to be hard because there's a lot of math. So I wanted to just walk through one math problem with you. In this particular problem, they give you pressure, temperature, volume, and ask you to tell them how much gas is there. A lot of students solve the problem like this. This is solved correctly, but if you write it down in your notebook and then you come back to it to study for the midterm, what are these numbers, right? You know this is not the best way to do your work in chemistry. It looks like a lot of work, but it actually saves you a lot of headache and a lot of time if you show all the steps You tell yourself in the future, what do all the variables stand for? What are the units? So in this case, pressure is 1.5 atmospheres. There's several different units for pressure. Atmospheres is just my favorite. Volume is 8.65 liters. N stands for the number of moles. As I said last lesson, moles will be our friend again in this chapter, so don't forget them. R is going to be something you learn in this chapter, which is the universal gas constant. It's going to be different depending on what unit of pressure you use. Your book likes to use kilopascals. I like to use ATM. It's easy, they'll give you that R, but in case you ever need an R with ATM, the number is 0.0821 latim per molk. I just said latim per molk because I'm lazy, but notice it's liters times atmospheres on top, moles times Kelvin in the bottom, in the denominator. That's where those units have to be. Dimensional analysis is your friend. If you keep your dimensions, liters, atmospheres, moles, Kelvin, they'll cancel out when you have the problem set up right, and that's a clue you did it right. Temperature is given to you on these problems, but I just wrote TF minus TI because you want to remember if you ever have a range of temperatures like you will a chapter from now, always do final minus initial. And K stands for Kelvin, which is based on that kinetic energy of molecules you learned about last chapter. The beautiful thing about chemistry, it all builds. So if you ever need to go back, do it. That's part of learning chemistry. Our equation is PV equals nRT per nert. It's an easy way to remember that one. Use your algebra. I never learned algebra really until I started doing chemistry. Just do your algebra. The chemistry will work out. So I rearranged PV equals nRT to solve for n by dividing both sides by r and t. So the equation that's going to be helpful is n equals PV over RT. Now make sure that this next part makes sense to you. All I did was plug in my variables from up here into the correct spot. I just substituted them. But I also canceled out units for you because the R units sometimes seem mysterious, but they're not. 1.5 ATM times 8.56 liters divided by 0.0821 liter atmospheres per mole Kelvin divided by 273 Kelvin. I said divided by for both numbers in the denominator because if you type into your calculator 1.5 times 8.56 divided by 0.0821 divided by 273, you're going to get the right answer. Don't multiply a number in the denominator. Also look, atmospheres over atmospheres cancel out. Liters over liters cancel out. Look in the denominator. Kelvin in the denominator, Kelvin on top, Kelvins cancel. That leaves you with 1 over 1 over moles. What is 1 over 1 over x? X. What is 1 over 1 over moles? Moles. Nothing tricky, just algebra. You can do this section. Bye.